So with that being said, there's just a lot of stuff that we do. There's a lot of places that we go to, so different websites and different stuff that you're having to navigate through. Um, so just to kind of help give you a run through. Are you done?
Yeah.
Come on, bring it on up. Um, in the past, students were able to earn, along with their degree, their diploma, and whatever that might be, they were also able to get NIMS certifications, which is the National Institute for Metalworking Skills, in every lab class that they had. So that might have been measurement, materials and safety, job planning, benchwork, and layout. Some students are bringing those things with them. It's CNC operations, CNC programming for the mill and the lathe. We've added now CAD CAM, so computer aided manufacturing are here for your son stuff, right there.
Thank you.
Yep. So, and then on top of that is the stuff that we've been doing in our morning class of.
Did he have a computer?
I think he was using my computer.
Okay.
So, yeah. He said his was full of porn. So,
Oh.
no, I'm just kidding. No, he's it.
Awesome.
No, but I think he just had my computer. So I put it back up in there. So, but as far as I know, he did not have one of his own in here today. Yeah.
Thank you.
Does like all mine from like CPA transfer over?
Everything transfers over. Really cool thing about all the certifications that we do is they are not really owned or governed by State Fair. They are yours that we partner with outside companies. So NC3, so the PMI stuff that you guys are doing that you finished up this morning for all of our 101s, you guys get a boatload more than everybody else does. So you're getting 6 of those, and then when you do, possibly at the tail end of this class, we might do some more, which is advanced measuring instruments. You got Haas, CNC lathe operator, CNC mill operator. You got a chance to earn with your degree or diploma an additional 10 minutes was a die check at Maxion. So, so that was awesome. So that is the goal for you guys. We will get you in front of potential employers. We partner with some people. Nucor is going to come out. They need to do some custom 3D printing instead of sending them out to an outsourcing 3D printing place. I told them, I said, why don't you guys just come here and you design it. You bring me the STL files. We'll print the stuff for you. So those are just the partnerships that we have with a lot of the places, and Nucor's a good job. So low level of work, high amount of pay. So it's pretty awesome. So okay, well let's get through. This will be kind of getting through this set of the book stuff, and so it's going to be 12, 13, and 15 will be the areas that we cover. Let's see, do you guys have that active? You don't, do you?
No, I didn't see that.
I'm going to go ahead and open, I'll show module 2 for you. Whoops. I'll turn these two things off. I'm actually going to shove this up into module 1. If you refresh, you should be able to see module 2. And you should see unit 12, 13, 15, book with measurement lab. So each one of these is broken into a chapter.
Come across my metrology book last night.
Yeah.
Is that?
So what I've done is I've taken parts out of the best parts out of books and used those in there. So, so it's yes and no. It's not the whole book, but it's parts of the book. Like I just wasn't in love with all of the components of all the books that we have, but I liked something out of each one of them. Okay, so we're looking at machining details as of now. Everybody is good with getting into Canvas. Everybody sees. Let me just go back. I'm gonna go back real quick just so I don't forget later on. So you should today, tonight, whenever, you're gonna jump in and do this module 1 quiz. And you just need to have that 62 points. You need to have that quiz done before 11:59 on Sunday night. Okay, submit it anytime. You cannot call and ask me questions at 11:30 on Sunday night and be like, "So Justin, how do you log into Canvas?" You can't do that because I'm not going to respond. Like it won't be like out of spite. It's just I'm not that quick enough to respond. So if you have a question though, tomorrow, Saturday, you're welcome to email me, and some things I see really fast, some things I don't. So it just depends on what I've got going on. I'm happy to respond to any of your questions. Most of these things should be questions directly from the book. If you are writing down the answers, then they are literally the same questions that we've covered in class. Okay, so nothing should be new to you. It'll be a little bit more because this was originally in Module 2, but I'm just shoving it up into Module 1, but I won't ask you any questions about 12, 13, or 15 until next week. Okay. Any questions on that? Is everybody taking an online quiz or anything in Canvas before, or at least in some kind of online something or another? Okay. May just before you leave today, you may just open that up and make sure that you can get in there and get to it. I do not have that set so that you can take multiple attempts. That's a good question though. Okay, so when we're looking at machining details or features, we're going to look at things like the terminology of boss, dovetail, flat groove, key seat, keyway, neck pad, slot, T-slot, and groove. And so these are just terminology that we would use in order to define different things that we're going to use. But it's just like anything, every kind of set of skills has some terminology that goes with it. So when I say we're going to cut a key into something, or there's going to be a boss on something. A boss is something like an island that sticks up. A keyway is a groove that's set down in a shaft, typically for some type of a key. So a shoulder or a neck shoulder would be an undercut area. Why do you think that something like that would be beneficial to have?
So you don't have a radius, for example, when you're going into a counter bore.
Sure.
Holding your bolt head officer.
Could be putting thread on it.
Yeah, a couple different reasons. It can be thread relief, so that when you're threading, you can get good threads all the way back, so you can bottom it out on that shoulder, or on the shoulder of the head.
Could be for a snap ring.
Could be for a snap ring, O-ring, quad ring, something like that that might go inside of there. Yeah,
Less likely to corrode against the material.
possibly. Yep. Another one would be just so you can, and it's really what John was saying in the beginning, so you can get, you don't have a radius in that corner, you can get all the way down to the bottom of it. The option for this is to leave some kind of radius on there. So this has pros and cons to it. Something square shoulder like that, where it has no radius in there, any type of square corner, 90-degree corner, is an automatic break or fracture point. So you want to make sure that you can, if you can, a better scenario would be to do something like this. For the most part, same functionality, unless it's a quad ring. Yeah.
So something I noticed we started doing on one of the dies that our guys built is rather than trying to get a square corner on the head of a punch, they would just go ahead and mill or countersink or whatever
The hole.
the bore that it sits in. That way.
So like you might.
Breaks over that way.
So like looking side view into it, you've got a plate and it just does a little thing like that.
Yes. So that would be the cavity for a punch head, for example.
That way when it went in or came out, if it had a little radius, it still sits down flat. Is that what you're saying?
Yeah, except they put the radius on the inside corner of that counter bore as well. That way you don't have to worry about it
Like that.
creating any clearance issues.
Yeah.
Radius on both. Too much or whatever.
So adding a radius leaves some great strength qualities. Almost all of your insertable turning tools, or milling tools are gonna have at least a 15 thousandths radius on. 15 isn't much, but it's better than nothing. 30 would be your next common choice, so you go 15, 30, 45, or 47. So having some undercut in there is beneficial to what you're doing. Here you can see, if it's got the radius, it cannot seat down. If it's got some kind of an undercut in there, it is able to sit down. So several different reasons why you want to put something in there. Now, a lot of times on the print that we're working with, sometimes it's got really good clarity as to what they want you to do. So this says 125, 125 wide groove by 125 deep. Okay, just by looking at that, do I know if it's saying 125 smaller on the diameter or 125 from here to here?
It's saying 125 from there to there. So it's
From here to here?
yes.
So who says it's a difference of 125 in diameter? Who says it's like this? Who thinks it's diameter? The rest of you.
It's the same thing.
It wouldn't be the same thing. One of them 62.5 thousandths on each side. One of them changes the diameter by 250 thousandths. One of them changes the diameter by 125. But it doesn't say. And so you're leading, or you're leaving your operator or machinist into a spot where they're unsure of what to do. So a better definition for that would be, I want this diameter at this groove width. No questions asked. I know exactly what it is that they're wanting. Typically, an undercut like this has not a ton of great value. So you kind of plunge in, come out, quick caliper check, don't spend much time on it, and just move on. So it's not something that you're going to hold close like you would the diameters of something. And so here's just a couple of different styles of grooves. Internal, probably snap ring, O-ring. Here's some external wide grooves. You can have O-ring grooves, air grooves. You can have snap ring grooves. You can have oil lead grooves. You can have lots of different areas to be undercut through there. And again, here's a 125 or 182 wide, 125 deep, or a 125 deep, or 125 wide, sorry, 250 diameter. So just a couple different design styles of how that groove might be laid out. All right, so let's look at slots. Let's really look at slots and keys. So here we have a pulley, or sometimes called a shiv. So this is a pulley that might go on, run a belt. So some type of V-belt pulley. It's got a diameter, or I'm sorry, an angle for the width of that, and then a dimension here for the width of the bottom of this groove. If I know the width and the diameter of the groove, or the depth of the groove, and the angle, I know what it comes out to. So I don't need a small width here and a wide width here, because I know this is where it starts, this is the angle, this is how long it is. I can do a trig function and figure out the rest of it on there. Typically, whoever's drawing your stuff, engineer, draftsman, draftsperson, whatever it might happen to be, they're going to try to keep the least amount of dimensions on the print that they can, just so it's not super muddy. So when looking at key seats or slots, a couple different ways to identify those. How wide is this slot? What is the overall length of that slot?
What's the radius? Half of 750, right?
It would have to be half of 750. So your radius times 2 is 375. So they didn't have to put it on the print, right? So they're showing you that it's radial on the end. You know it's full radius, so 750, that means 375. take 313, add 750 to it, that's how you know what your overall width is. Okay, so there's just an assumption of you knowing how to do the math on these kinds of things, and so you shouldn't have to go to somebody and go, hey man, I'm not sure how wide this is supposed to be. So they're gonna look at you and go, really? Because it's right there, you know? Now, you can see it sometimes the other way. So let's look at the bottom one here. I'll pull it up just a little bit higher. So now, still 750 wide. Overall length is 2 inches and a 16th. Full radius. Now I know my full length on it. So same information, just a different way to present it. So how your person that you're getting prints from does the designing matters, and you'll start to figure those kinds of things out, the style that people have. All right, so groove like this that'd be cut on the shaft, just some type of profiling tool is going to be turning this out. Sometimes a form tool, but oftentimes not. Dovetail or a T-slot, there is a special cutter with the shape of the dovetail or T-slot that creates that. But you have to go in first with the normal end mill before you go in with your T-slot. Your T-slot cutter does not have cutting edges in this area, so you need to come through straight end mill first, then T-slot out this section. I have seen people run the T-slot cutter up to the end of those cutting edges to that diameter, and they're like, this thing won't cut anymore. And I'm like, is that a serious statement? And so like it's just like round hardened shaft up against part. And I'm like, dude, you gotta slot that thing out first. And they're like, oh my gosh, I knew that. You know, I'm like, okay, that's cool. Same thing here. You need to slot this thing out with square end mill, and then come in with your dovetail cutter and create the dovetail from there. All easy mistakes to happen, especially if you're in a hurry, but you want to make sure that you're grabbing those things as you make those. Several different dimensions that can be put across there to help you understand that. So here's a key seat keyway. So key stock is typically bought, so it's a purchased item rather than something that's made. Sometimes you have to make a step key or some type of modification. So, but typically key stock is made in a certain way. It's a really, really low carbon steel. Why would it be made? So it's cheap. Why would it be made cheap?
So you can replace it easily if it breaks.
If you want it to break, right? If there is a break point, that's what you want to have happen. If that shears, it saved you from having another problem. You figure out what's going on, you replace the key, the cheap part, you're back in business again. So same keyway, coupling, something like that, built-in breakpoints, those are important. So key stock is typically something we'll purchase, not create. A key seat is something that we're going to mill into the end of the shaft. Keyway is going to be something that is a shape that is put into a shaft. How in the world do you think you get a shape like that into a shaft?
Not with broach.
Sure, broaching would be a great way to do it.
You can mill it in too, I guess, kind of.
Depending on the width or the depth.
Yeah, depending on the sizes that you were working with, you could do some type of milling operation. So let's just say we've got our shaft like this. Okay, so that's the outside of it. Here's our hole. If we had a keyway like this, pretty good chance we could probably do some milling operation on it, depending on how long it is. Broaching is the process of taking a formed tool that's staggered and pushing it through with a press to create that shape, okay? So typically you'll run it through, pull it out, shim it, run it through again, pull it out, shim it, run it through again, then it's the final size. So it's kind of a tapered, jagged teeth kind of thing. We've got some 101s, you guys will broach a keyway this semester, so.
The only other way I could think of it, you could do it in a file, right?
One other way, I don't know what one. Yeah, one other way of doing it, well, maybe there's probably more than one other way of doing it. Yeah, you could file it, but boy, that's some forearms right there, man. I'm not filing it. I'm way too old and weak for that. So, EDM would be another one. So electrical discharge, machining process would do it. So, you guys, we use EDM keys all the time, especially big ones, so.
We was running these parts a couple weeks ago on like the CNC lathes, and they was like broaching them.
Broached them on the lathe, yeah. So here's a great story about this. So we figured out, so I used to work where he works now. And we figured out that we could create keyways on round parts in the lathe, lock the spindle, and we would just run these tools in there and just rip that thing to death, you know, over like 1,000 cuts, like 1,000 per pass. Took like 2 seconds. I mean, we were high-fiving and chest bumping, man, when we were done. And we were like, dude, this is so awesome. This is like easily 15 years ago. And I was like, dude, we just like created this thing. Like, we're so smart. Turns out people have been making it like that for like 50 years, you know, and I was like, oh my gosh. Sometimes you just don't know, though, you know, and then, like, I was telling somebody about it one day. I was like, dude, we're broaching on the 2-axis lathe, and they're like, okay. I was like, no, man, I said, we got like a form tool, and we like silver soldered it on the end of it, and then like we're just like broaching this thing out, and they're like, you know, you can buy broaches like that for a lathe, and I was like, yeah, but this is like a 2-axis lathe, we just lock the spindle, and he's like, yeah, that's exactly, like pulls it up on his phone, he's like, here you go, you buy it for like $12. I was like, oh my gosh. It was still cool, we totally thought, it was like, a year ago, you just invented a car, and you're like, check it out, you can get in this thing, it's got an engine and wheels, and everybody else is like, a car? No, that's not what it's a horseless carriage. You know, you're trying to explain to them, like, a car, like, that's existed forever, and you're like, well, yeah, you could call it that, and then you're like, oh my gosh, these already exist. So, anyways, you're talking about having your bubble bursted. We definitely had it bursted that way. But it's a great way to do it. So, if you can do it right there on the machine, what you're always trying to do is you want to get parts off least amount of touch that you can have on it, least amount of operations that you can do. Great thing about doing Keyway on the lathe is it's usually you don't have to worry about center line issues, lines up pretty good. It's just a really smooth process. So some keys will be trapped inside of the shaft, some keys will have an entrance point from the end of the shaft. Difference kind of between a keyway and then a key seat. So your keyway does not, or your key does not have to be rounded on the edges. It can go into something that's got rounded edges. That keyway is pretty insignificant as far as details. It just needs to function. Okay. Woodruff keyways, same thing. They're a little bit different. You really need a Woodruff key seat cutter for that, so a special cutter. They're typically numbered out by, or they're identified by numbers, so 1, 2, 3, 4, 5. A lot of times you're going to see that that's like an electric motor shaft. Keyway is where you're going to see that a lot of times. Same thing, the keyway is meant to break so that you don't destroy the motor, the shaft, whatever it is. It's the weak point in the whole system so that you don't have another bigger problem. All right. Skip over. There's not a really good, talking about bosses. There's nothing really that shows a great example of a boss. I mean, this is okay. That's not exactly what I was looking for, though. So anytime that you have an area that protrudes up higher than the surface of the part is a boss. So think about an island on a part. It can have a hole in the middle of it. It could just be this raised up area on there. That's a boss that sticks up from there. So you got this slot going down inside of the slot. It can be all the way through, or it can be contained like a little swimming pool where it holds something inside of it. So a slot and a keyway can be the same thing. All right, let's truck on through, and if we want to, we'll come back with some questions later.
What about an emboss?
An M, it's like EM, like it's embossed. Okay. Yeah, we can talk about an embossment.
Kind of like the opposite.
Yes, so if something's embossed, it is typically, so like,
Kind of like a pocket.
yeah, but it's usually pressed into it. So if something's embossed into something, stamping is embossing. Yeah. It's a good question, though.
Is this a whole other
I'm in 13.
PDF?
Yes, yeah. So now I got smart about halfway through this thing, and I was like, I should just do this as chapters. And so I broke them up into chapters. So I'm into 13 now, section views. If at all possible, I'm gonna try to, I don't know that we can get through early, but we've gotta be done pretty close. I've got a meeting I have to be at this afternoon, so, which I probably don't really need to be at, but I've been asked to be there. Yeah, I'll probably go there to sit through it, and they'll be like, we actually changed our mind, we don't need you. And so, okay, thank you, and then leave, so, which is fine. Alright, so we're gonna talk about, section views. I'm gonna go back up to the top for the literature, the key terms. Break lines, offset sections, broken out sections, cutting planes, remove section, revolve section, section line, section view, half section, full section, cutting plane, and cutting plane line. So there's several terms, and personally, I think that they can be a little confusing, okay? So, a cutting plane is an imaginary, or if we could break this part in half so that we could see inside of it. Imagine if you magically could saw it in half without actually sawing it in half. It's almost like you can kind of see the saw lines going across there. Those diagonal lines running through there, believe it or not, there is actually how they hatch those, whether they're crisscross or just diagonal, oftentimes means the material type. So you can actually look at that and see if it's a tight crosshatch, it means certain types of material. If it's an angle like this, mild steel. So there actually is some terminology that goes with that. So when we start to talk about section views, it means we're taking the whole and we're looking at a smaller section of it, okay? So like if there's something that's got a huge amount of detail in one small area, okay, so like I just printed this jaw, this is gonna go on one of our chucks for the robot, and like always, as soon as I sent it to the printer and it was like 14 layers in, I was like, that's not what I want. And so it was like scrap before it ever even made anything, but so it's a jaw like this. Opens and closes, grabs some 1.5" stock, moves it over into the next position. Now, a lot of this is pretty straightforward detail, but I might section view out some of this because you can't tell. It's got counterbores in it, but you can't really tell how deep those are, especially from this. You can't even tell if there's counterbores in there, right? So counterbore, remember, it's a larger diameter cylinder that comes down, and then the last 200 thousandths of it is a little bit smaller. It's got these little bitty metric bolts that go in the end of it, and so, yeah, as soon as I started printing it, I was like, man, that's not gonna work, but it did help me figure out exactly what I wanted. So this allows us to see inside of this part without kind of breaking it apart and having any kind of fracture failure problems. Okay, the way that it breaks out is the ways that the arrows indicate. So the arrows indicate the direction of view. So we're taking it and we're flipping it this way so we can see this side of it. That's your hole, this part of the hole. This is your gusset area, that's what you see right there. This is this hole, it's right there. Make sense? Okay. So you're gonna see a couple of different ways that you can section things out, but something like this will be pretty common. If it's sectioned out one time, it's section AA. If it's sectioned out 2 times, it's section BB. So 2 different sections. What do you think the third one is? CC, yeah, and it keeps going, right? So it's just to help you identify which section view am I looking at. Typically, features look different from each other, but sometimes features can look pretty similar. So it's about knowing, kind of where that is and tracing that thing down. Okay, here's just another section view. So here's what I'm talking about when I'm talking about these different lines that run through there. So they can see there's different styles and shapes. Gray cast iron or general purpose. You got steel, rubber, plastic, electrical insulation, titanium, or a refractory metal. Marble steel, or marble slate, glass or porcelain, zinc, lead, babbitt. Babbitt, anybody know what babbitt is? I will give you 50,000 non-credit bonus points if you even just guess at what babbitt is.
Mix between copper and iron, maybe?
Half right. So Anybody ever taken an engine apart, seen like the main bearings or cam bearings, stuff like that? Yeah. So that's not it, but that's what they used to be. Okay, so it's a solid kind of an aluminum brass, so that you can spin on there. It's not going to break down as easily. It's going to allow it to kind of lubricate. So like oil light, you might know what oil light is. Oh, where have you guys been? You heard of it? So oil light is oil impregnated brass. Freaking materials are so amazing. So they take brass and they impregnate it with, I don't know how they do it, but it sounds weird, with oil, okay? So it's full of oil. It doesn't seem like, you don't pick it up and it's oily, but if you start drilling a hole in oil will come out of it. And it's insane. So if you want to mess with somebody in the shop, you give them a piece of oil light, and you're like, hey, take this piece of brass and drill a hole in it. And they start drilling a hole, and they're like, what just happened? Like a quart of oil just come out of this thing, and you're like, what? That's the wrong stuff, you know. So, but that happened to me, and so it's already impregnated with oil, so that a shaft can run on it. Because not always can you fit roller or needle bearings into something, right? So like, take your engine. What kind of engine? Like a Chevy engine or like a Ford engine or like what kind of engine?
55 Willys Jeep engine.
Okay, all right, I can take that way better than Ford. So I just got done rebuilding a 350, and there was no way that I could put needle bearings, roller bearings, or anything like that in there. So you had to use engine bearings. I had chopsticks. So it's just too thin, right? So it's like 80 thousandths thick, and so there's no way to get a needle or a roller or anything like that in there. So Babbitt is just one of those materials that's an alloy essentially, and it's lead, zinc, or no, it's lead, bronze, and aluminum. I think is what it is, all mixed together, and it forms a really great bearing material. So. There's a lot of amazing materials out there. All right, here's a section view of a pulley. Typically, again, with lathes, you have round parts. You don't need to see multi-views for it, or more than 2 views, I should say. So here's the cutaway of it. You're seeing this side of it. You can see the keyway that goes through it. You have what would that be called?
Spot base.
Spot base.
Oh, yeah, spot
Yeah, it is a counterbore, but it's really more of a spot base because it really doesn't have much depth to it. Okay. So you have here a tapped hole to hold that keyway in. So going back to keyways, sometimes there'll be a set screw that goes down on top of that to help keep it down. It's hard to grab those sections right here because typically your key or your pulley or your sheave is up much larger. It's hard to get over to that flange to tap that hole. So there's actually a tap called pulley tap that's really long, recessed on the back side, so you get down into something, which can work for lots of other things other than pulleys. So that helps hold the keyway down, that set screw in there. Again, here's a section view. You're seeing this side. Okay, so what you're seeing here is this part of it. Section views are super common. You will not see any kind of section view stuff in 101s, but as you start to kind of progress, by the time you get to some of our upper level NIMS parts, you'll start to see some section views in some of our parts. Offset cutting plane is a great way to get yourself super jacked up and looking at the print. See how this does not go straight through there? It's kind of jig-jagging through there, so that you can still see all the features. Because all those features would still be there in 2D view, but just the cutting plane is just not straight through. So just because everything's on the same center line doesn't mean that it's not there. So you need to make sure that you're paying attention to those offsets. If you're lucky, you could get something like this with this isometric offset, you know, so you can kind of see the cutaway into it. Or they have this half section cutaway in there. So cutting apart in half is called a full section view. Cutting apart into a quarter is cutting apart in half in the full section view, cutting apart in a quarter the half section view. I've always felt like that was a little confusing. So half is full, and then full is or half is a quarter. So here, when you have section views like this, looking at all of these things, they actually kind of look like belts and belt buckles, don't they? I never thought about that until I just looked at this. So what this is so you know, because if you look at whether this is a Z channel, rectangular, an angle, or round, if you're just looking at a 2D view of it, you can't tell. This is telling you, this is tubing, this is Z channel, this is rectangular stock, and this is angle, so that you can see that from the part that you're working on. Here's a pulley. You can see from this section AA that this section is I-beam shaped. So you have an I shape that runs through here. B, section BB, is round. Okay, so that's probably a casting or forging. All right, so what am I looking at on this part? The top part.
The plunger looking device in the center of the row below it.
Okay. So on this section here, what do I got going on? I mean, are these slots here? Keyways through there? What? They're holes, right? So you got 2 holes going through there. You've got a hole that runs up and down through there. So yeah, you got some holes running through that part. So it's a matter of kind of being able to see what some of that breakout stuff is. Here we've got some information about this little recessed, probably oil cup area. All right, we're gonna move on. That's not what I wanted. Okay. This will be, so we'll end with this today, but we'll start with this probably Monday. GD&T, geometric dimensioning and tolerancing, is going to be something that flows through the rest of what we do throughout the semester. It's one of those things that I think that every shop does, but doesn't do well. The shop I came from, we would say if we weren't for sure about what the part looks like, or we weren't for sure about the function, or the feature, make it better than what it was supposed to be, and that, we talked about that before. But geometric dimensioning and tolerancing will help you make parts more accurately, and you should have more parts go through. You should have less scrap if you pay attention to what your GD&T says, because it's actually not saying you have to have perfect parts every time. It's saying, does it fit and does it function, and is it the right form? So form, fit, functionality is what GD&T is really comprised of. And so we'll at least do a high view over it today. There's a ton of information about it here. So you have angularity, you have basic dimensions. Basic dimensions on their own have no tolerance to them at all. Circularity, circular runout, cylindricity. Cylindricity would be that something is the same size on both ends of the circular. Datum is a feature point. Datum features and datum feature simulators. Datum feature symbols, datum target symbols. Features, feature control frames. Feature control frames is kind of the roadmap of what we would know for what we're going to do to a feature, a hole, a keyway, a flat, corner. Feature size, flatness, form, least material condition and maximum material condition, orientation, parallelism, perpendicularity, positional tolerance, profile of line, profile of surface, regardless of feature size, and then regular feature of size, runout tolerance, straightness, tolerance, total runout, or TAR, and then true position. Some of those things will kind of flow into each other. Some of them will be total standouts from themselves or from the other ones. All right, so when we look at form, orientation, position, profile, and runout, there's really about 14 symbols that are the most primary components of GD&T. Straightness is a feature straight, regardless of anything else that's going on. It is the hole straight, is the line straight, is the shaft straight, is the dimension straight. Flatness cares nothing about anything other than is this surface flat. It doesn't care about squareness, it doesn't care about perpendicularity, so it could be crooked, but is the surface flat? What happens is when we start to look at flatness is we start to say, well, how flat is it to this, how flat is it to this, but what we're doing is mixing up terms, and so we want to make sure that we're staying with correct terminology the whole way through. Circularity, how round is it? Okay, so even this roll of paper towels, even at this state right now, has a circularity tolerance to it. So would you say that's circular? I would say it's circular, but like, at what point is it circular? You know, is this circular? Kinda. At what tolerance or what point is it circular? So it depends on what it's really asking you for. Cylindricity, is this diameter the same size as this diameter? If it's not, if this end's smaller, it's taper, right? And so let's just think about where that would affect us. Imagine if we have a big long conveyor belt and our rollers on there are tapered. What happens? Pushes the belt to one side, right? Causes everything to run one way. So say you got a skate wheel conveyor and you're trying to run some parts through. So a long time ago, I worked at Long John Silver's when I was 16. I feel like I made the best fish and chicken that any 16-year-old ever made. I also was the guy who unfortunately had to do the truck a lot of times. The truck is like, if anybody work fast food? Yeah. The truck is the best and worst gig in the world because when you're in certain parts, it's the right temperature. In other parts, you go hot to cold and you're gonna make like one pass out. So if you had a roller, so they would back the truck up. Anybody ever done the truck where they kind of back the truck up? They got the conveyor that runs out, and the guy's on the truck, and he's just laughing as he's just trying to shove as many boxes at you as he can. You're like, slow down, I'm 16, you know, and he's got like a bazooka shooting these things at you. And so what would happen to us is sometimes these conveyors would be crooked or tapered, so 2 inches here, 1.8 over here, because they've just been worn to death. And so the box of fish would stop right before it hit the cooler where I was inside and just fall, and he'd be like, that's on you. I was like, how is that on me? I have not even, like, I couldn't touch it if I want to. He's like, I didn't make that happen. I was like, you definitely made that happen, but I don't own that conveyor. And like, the 16-year-old making at that time $4.25, and the truck driver, I wasn't winning that argument, you know. So I had this whole like pile of melting fish out there, and so you bring in a little bit, and then you run outside and you shove them back in, and so that's the problem when you start to have that taper in there. Now, was it dimensionally right when the person made it? Well, probably worn down over time. Now, if you're not paying attention, you can just measure those right dimensions and slip it past QC and it goes on by. It doesn't make it a right part. So you want to make sure you have the right part. Angularity for me, I learned a lot about angularity over the summer. I always thought it had more to do with angle, 30 degrees, 50 degrees, but it really has to do with what's the consistent angle between the surface and the surface, however much waviness that this has, however much waviness that this has. What's the average angle that's going between those two things? Perpendicularity, how close to 90 degree is it? Now on a short part, you can be out pretty good on perpendicularity, right? So if you got a part that's like 1/4 inch tall and it's got 3/1000, no big deal. If you got 3/1000 on a part, so let's do it by degree. If you have 1 degree out of perpendicularity on a part that's 1 inch tall, it's not that big of a deal. If you have 1 degree out of perpendicularity over a part that's 44 inches tall, makes a huge difference, right? So if you can see it. And so perpendicularity matters. parallelism, how equal are these two sides? Now, so earlier we looked at flatness. And oftentimes when I see students do this, is they might put something on a granite table's all over there. They might run an indicator over the top of this, measuring flatness. They're not really truly measuring flatness. What they're really doing is measuring parallelism, because they're measuring it to the table, right? So they're saying, how parallel is this to the table? So flatness is really the amount of dips, highs, and lows within the surface. It is essentially the same check, but you're really checking parallelism, not necessarily flatness. So really, to get a good true flatness measurement, you really need to be able to probe point all this surface to see the highs and lows, or some other way of doing it. You can do a dichrome fluting or something like that to figure out the flatness of it. But for most applications, granite table indicator will still function. It'll still do pretty much what it's talking about. Position or true position. Where is this position located in not only X and Y, so Y and X or Y and X, but in angularity, where is it at too? So the hole could just be up like this, down like this, over like this. Where is it at, not only in X and Y, but in the position of where it is? One really cool thing about GD&T is that if you've got a pin that goes into a hole and it doesn't fit right, I kind of struggle with this being okay, but I do understand what they're saying. If your hole's off position and your pin doesn't fit into it, if you have the right amount of tolerances, GD&T says, make the hole bigger. And the pin still fits in there. And I'm like, that's actually right. Like, according to the print, lots of times, like you may have to make the hole way bigger, right? But if it's you can't get the pin in a trailer hitch, who cares positionally, right? You just need it bigger. That's why, I mean, we're like that all the time. Who has drilled a hole and then went to put a screw in it and it didn't fit in there? So you took the cordless drill and you just did this, right? Yeah, absolutely. Because positional didn't matter. Diameter mattered. And so you got it through there and you're like, I'm good to go, you know? Which really, what you wish you would have done was just drilled it the right size the first time. So that's when we start to look at position and positional tolerance and true position. Profile of the line. So the waviness of a line or surface. Okay, so we're looking at the highs and lows of that. So not just the average of it, so we're looking at the highs and lows. Circular runout, total runout for us will be practically the same thing. I might call that TIR or total indicator runout. So if you're working on a lathe, and you will be working on the lathe, if you turn one side of something and then turn it around to the other side, chuck on it, and start machining on that side, you oftentimes don't have concentricity, right? Because that only works if you indicated two diameters or a diameter and a face in order to make it square and parallel, or square perpendicular, so that things would be concentric. And so when we have when we just slap it in the chuck and then flip it around and slap it in the chuck again, we get this cam kind of thing. Or if you've turned two diameters and they don't match up right, hoping that they do, like you're turning an inch and a half, you turn an inch and a half, and you're like, it's like shadow, and it's like highs and lows on there. Concentricity is total indicator runout. So you put your indicator on there, and you're like, well, the shaft I just turned is running true as a string, but the shaft that was already turned before has 8/1000ths runout. Okay, so your total indicator runout is 8/1000ths. When we turn shafts or parts on the lathes, we care about center line or concentricity, because now that part that's got 8/1000ths runout is 4/1000ths off center line. It's probably going to be a problem for us. So we want to make sure that we know what we're doing. So we know what our circular runout and total runout tolerances are. Okay, datums are primary most important parts. The quickest way to figure out what the most important part is it a datum? If it's a datum, it probably matters. If it's got an A, B, or C on it, everything is probably tied to it. So when you make dimensions, when you check dimensions, You need to make sure that you're checking to that so that you can make sure that it works right. Datum A is typically our primary or largest surface, B is our secondary surface. Here we're saying something is has angularity tolerance of 5 thousandths to A, okay? Here we see this face needs to be perpendicular within 5 thousandths to datum A. Here's datum A. This surface perpendicular to this surface, no matter what size that happens to be. Now, in my mind, I don't know that I love that because as this part could grow or shrink, 5 thousandths means something very different. So sometimes I would maybe say that would be better for an angular tolerance. Geometric characteristic of flatness, parallelism of 3 thousandths. That part's got to be parallel within 3 thousandths. Let's go past some of these things. Let's go to maximum material condition. Let's see, there should be at least material condition as well. Maximum material condition modifiers. So let's talk maximum material condition. So when we're talking about MMC, and it'll be in a feature control frame as well, MMC and LMC, which is maximum material condition, least material condition. Maximum material condition on a whole would be the smallest that it could possibly be within tolerance. So if you have a hole, my maximum material condition is 1.495 because it's got the maximum amount of material that could possibly be in it, okay? So that's my maximum material condition. My least material condition would be, my LMC would be 1.505. Get the least amount of material in it. If I am at a maximum material condition, being the smallest size, leaves me with a lot of room to do some stuff. I can shift that hole if I need to, I can move that hole, I can tweak that hole and do some things. If I'm already at my LMC, I'm kind of screwed, because I have to start to go bigger, I have to then start taking it out of tolerance. Now, GD&T gives you oftentimes something that's called bonus tolerance. If my feature control frame said, let's say that this is A, and that this is B. If my feature control frame said that positionally I needed to be within 5 thousandths to A and B, and I'm already at 505, I've got a little bit of a problem. But what I can do is take this 5 thousandths and I can start to stretch that diameter out by at least half of that, gain some bonus tolerance, and kind of split the difference on where some of those problems are. So I'm at 505, I'm out a little bit positionally, I might go up to 508, and then squeeze it just a little bit over to one side in either X or Y, and be able to bring myself back into where I need to be. Really is gonna help you save a part from being scrapped. And it's gonna matter a lot to you if you'll start to think about those things. The number one problem that students have, not number one, this is what students do a lot. You guys who have been already machining with us see this all the time. I'm making my part, I made something wrong, what do I immediately do? Scrap it and start over. How many of y'all have done that? Just made something, immediately went to scrap it, start all over again. And what you ended up doing is throwing away a part that was like 90% good, that could have been shimmed, it could have been plugged, it could have been modified, you could have tweaked a dimension somewhere, but what you said to yourself was every dimension wasn't right. But GD&T is saying, is the overall functionality of the part still good? Does it still do what it's supposed to? And then yes. And so the problem with doing that is making the part, having it not be perfect, and then throwing it away is you've lost all of those hours of machining. So you got 6 or 7 hours. So our 104s, they had a really hard time with that this past year. Make the part, As soon as there was a wrong thing with it, just throw it away and start over again. And like, I think if they were to go back and look at some of those parts that, like now, they would have been like, oh my gosh, I probably could have tweaked this here. I probably could have made this right here. Like, I've done it before, especially when you start to get in a hurry or get nervous about something. You're like, oh, junk, throw it away and go start over again. And then you're like 2 days later, you're like, I think I could have saved that part. And you're like, it's too late now. So before you go to the trash with a part, stop, get your bearings, think about it, talk to somebody. Hey, is this savable? Can I plug it? Can I fix it? I don't really want you guys to weld up surfaces and remachine them. That's janky, right? So I want you to, like, if we're 90 hours into something and you jack a hole up, yeah, we'll probably do that. We'll weld it up, or if we can't make a sleeve for it and fix it. Yeah, that's fine. We do that all the time in the world. But I want you to make good parts right the first time all the time, but I also know that doesn't happen. So we got to stay within our tolerance zones of things. But just don't react too quickly and cause yourself to spend more time working on something. It's okay to be methodical about, these are the processes that I need to do. I would encourage you to write down the steps of what I'm going to do as I do it. I got this piece of material. I'm going to saw it. I'm going to saw it to this length. I'm going to do this. I'm going to do that. I'm going to do this. It's going to take these tools. Make sure that you do those things, and then you'll find yourself being really super successful in what you do. Now, mistakes will happen. Don't be surprised by that at all. ASME Y145, again, that's just that kind of code that we've been seeing over and over again. These are some things, when they make some changes in GD&T, this is how you'll see that listed out. Things that matter and things that no longer matter. Feature control frames, I've talked a little bit about feature control frames. So this would be symbols for maximum material condition, true position with 10 thousandths, maximum material condition, true position, 5 thousandths, maximum material condition to A and B. Okay, so those two datums on there. Here's just some examples of how that works in moving some of those parts around and gaining up some free or bonus tolerances there for you. Okay, so straightness and flatness. And then let's see, what else can we look at? There's flatness and flatness, or parallelism symbology. So here's how circular this is, how round this is. We talked about that a little bit. We talked about cylindricity some. And so these are just the overviews of this. We're going to see more of this as we go. Angularity. Angularity has more to do with the surfaces rather than just the pure angle of it. So like on a part like this, it calls out to be parallel within 2 thousandths. And so what we might find is this dimensionally correct here and here. This wall might be straight. This wall might not be straight. We'd probably come in and fix that before we would go in and just destroy that thing and pitch that. So you want to make sure that you're really taking the time to do some good inspection on parts. Some of that stuff isn't going to work for us. We'll take care of that. We've talked about that. Man, you guys are like blowing through this. That's just some worksheets on 15. Okay. So here's what I'm going to do. I'm going to stop here, and we're not going to do the worksheets on this. All you've got to do is do the quiz. Okay. Log in and make sure that you can get to the quiz before you go. If you're familiar with Canvas and okay with Canvas, done a quiz in Canvas before, you're good to go. You get one shot at the quiz, and 62 questions or 62 points, I think is what it is. Starting Monday, we'll start stepping up some of the stuff that we've done. We're going to start doing some things, so I'll have parts for you to measure. And we'll start working on rock welding, heat treating, understanding some material types. And then we probably won't be on the CMM until probably week 3. I'm hoping to get the other 2 CMMs in before we start working on those. If not, we'll start working on the CMMs that we've got. This entire class, unfortunately, is a lot of us in here, so not out in the shop. So it'll be a lot of modeling work and some other stuff that we do later on. So this is probably your one and only sit-down class that you'll have with us during your time here. So you gotta bear through it. But okay.
Modeling as in CAD stuff?
And the CAD stuff. Yeah. So that's some people, that's their jam.
I love it.
But yeah, I do too. All right, so you guys are good to go? Yes,
The module 5, please.
the module 1 quiz.
But we do need to do some MR stuff too, correct?
Yeah.
Safety for machining
Yeah.
and whatever.
Yeah, I think that's in. Yeah, so I gave you you're looking at the 0.5 quiz. So that is immersive. So make sure that you get into immersive and get into MACH105. Do that before you leave. So you need to have your immersive stuff done. That's the 0.5 module. And then the quiz done in module 1.
A lot of cheap dust collection system.
You did?
Yeah.
Thank you.
I had a question for